Hello, this is Gigi from Kauai Community College. This is the second video on the precise definition of limit. In this video, we will be focusing on finding delta. Okay, so finding delta is what we're going to focus on. So make sure you watch the first video on the precise definition of limit before this one. All right, so let's again review what the definition is of limit. The limit as f of x as x goes to a is equal to L if and only if for all epsilon greater than 0 there's a delta such that for all the x that are within the delta neighborhood, that means the absolute value of x minus a is less than delta. If that is the case, then f of x minus L will be less than epsilon. Meaning if an x value is within the delta neighborhood of a, then the f of x value will be within the epsilon neighborhood of L. All right, so let's take a look at how we would prove using the definition. So as we talked about, step 1 is to find delta, and that's a pretty important step in this proof, but it is not part of the proof. It's just your scratch work basically, because you have to show that there is a delta. So we have to come up with a delta to claim that, hey, there really is a delta that would work for all epsilon. So in this step 1, which is what we want to focus on in this video, we are going backward to show what delta is given some arbitrary epsilon. Okay, and then step 2 in the proof is to go ahead and write a proof, which is an actual mathematical essay to convince someone that this is true according to the definition. So let's take a look at some particular examples so that we can really understand how to go about finding delta. Okay, so we're going to take a look at this function here. That's f of x. Okay, according to this picture, we're going to label some things here so that we can actually understand the definition. Looking at this, we would say L is 3. That's what we're going to try to prove that the limit is. Okay, and this particular epsilon that is given to us, remember epsilon is an arbitrary neighborhood, and it's given to you. Okay, so this actually is one particular example of an epsilon. Suppose in this case, epsilon is 0.5. Okay, that is why we have the absolute value of f of x minus 3 is less than 0.5. The absolute value of f of x minus L is less than epsilon. Okay, so if that is your epsilon neighborhood, we will want to know what is that delta that is going to make this work. In other words, we go and we look at this right here. We would say, hey, to translate what is going on, A is 2. And as you can see, that delta was claimed to be 0.79. I want to go ahead and explain where that comes about, okay, and what it means to find delta. So given that epsilon is 0.5, okay, we want to know how far away can we step to the right or to the left of A, meaning what is that delta, so that for all x value within this delta neighborhood here around A, that f of x will be mapped onto the epsilon neighborhood near L. And L in this case is 3. Okay, so what is that delta that we can force all the x's within that neighborhood to have all the f of x within that epsilon neighborhood? Okay, so according to this function, if we go and graph the f of x value right here. So we're looking at what is f of, in this case, 3.5, right? F of 3.5, it turns out to be 2.79, and then f of 2.5, which is the other end right here down, is at 1.21. Now, if you look at the graph is symmetrical with around 2, right? And you can see that delta 1, meaning on the right hand side, the delta distance is 0.79. On the left hand side, the delta distance, that distance from that value to 2 is also 0.79. Well, that makes it easy. What are you going to choose your delta to be? Well, just let delta be 0.79, so that whenever you have an x value, say right here, well, f of x is going to map right onto f of x is going to map right onto the epsilon value, right? So therefore, we're forcing all of these values to be within that really tiny small distance epsilon. So the definition said if we can find a delta that will make all x, no matter where x is, even if it's here, you can always stay within that delta neighborhood. Then the limit is L. Okay? So here we choose delta to be just whatever that distance is because it's symmetrical around 2. Well, what if the scenario is like this? Okay, so let's just take a look here for a second. Your L is 3. Okay, and for this particular example, suppose epsilon is 1, meaning you're stepping one distance, 1 unit away from L. Okay, that's actually is a pretty big value for epsilon. But just for the purpose of having nice numbers to take a look at the definition, we'll go ahead and say, hey, let's epsilon be 1. Now, can we find that delta? And how are we going to find that delta? All right, so what does it mean to find that delta? First, your A is 2. And then the question is how far, right? So the question is, how far can I step away from 2 to the right? And how far can I step to the left? What is that delta value that will work for all x? Okay, whatever that delta value is, it's going to be symmetrical from left to right, right? And as you can see, you could actually walk away from 2 pretty far to the right, but not that far to the left because of the way that the graph is situated. So there's a little bit of manipulation here to make that f value to be within that epsilon neighborhood. Okay, so let's take a look here. On the right, the boundary is 4. However, on the left, the boundary is 1.5. So to the right, that delta 1 distance is 2. Whereas to the left, the delta 2 distance is 0.5. So when choosing a delta, you are choosing a delta, not delta 1 and delta 2, right? So when choosing a delta, we would say, well, we gotta just pick the smaller distance so that we can force all x's into this epsilon neighborhood. Because if we chose the distance to be anything bigger than 0.5, say if we choose for it to be like 1, well, then if x is right here, well, f of x is over here. And it's outside of the epsilon neighborhood. So that's not going to work. So we need to choose delta to be the smaller of the two. So in this case, delta will be 0.5, or anything less than 0.5 is going to work. Okay, so delta would have to be 0.5 or less when epsilon is 1 for this particular example. Okay, so the lesson here is, the essence of this slide is that when the graph is not so symmetrical, we need to choose that delta to be the minimum value of the distances, so that we can always map. We can always map wherever x is. F of x will always be within the epsilon neighborhood. Okay, so we're not going to go all the way out. We're only going to go right here, just 0.5 distance away from 2. And that is what we will let delta be. So how does this all work out in a proof? Okay, a good function to demonstrate the fact that when things are not symmetrical is a quadratic, right? As you know, a line, linear, constant rate of change, whereas a quadratic is not a changing, it's a changing rate of change, right? So let's prove that the limit of x squared minus 1 is 8 using epsilon delta proof. Okay, so let's write down first what it means. In order for the limit to be 8, we would say for all epsilon greater than 0, there's a delta such that if x is within delta neighborhood of 3, in this case, a is equal to 3, okay, then f of x minus L, which is 8, has to be within that epsilon distance. So x squared minus 1 minus 8 is going to be x squared minus 9. And that is how we got the x squared minus 9. So we'll go ahead and say step 1 before we write the proof is to go ahead and find that delta, meaning let's do some scratch work, go backward to find out what that epsilon, what that delta is for any given epsilon. Okay, so how do we work backward? We know, and in the end, that we want x squared minus 9 to be less than epsilon. Well, x squared minus 9 can be factored out to be x plus 3, x minus 3. And you can see the essence of this right here, right? That's relationship right there. So the delta is going to happen somewhere right here. The question is, what is this? X plus 3. Well, we're going to pause right there for a second. We know that it's not symmetrical, so we know we're going to have to do some restriction, right? So here, x equal to 3. Here, L is 8, right? So for any given epsilon, that's 8 plus epsilon. This is 8 minus epsilon. We want to match and find out what that delta neighborhood is. And as you can see, it is smaller distance on the right than the distance on the left. So we know we have to take a minimum of the two distances. But what is that exactly? Okay, how do we manage that? Here, I just need to know what my x plus 3, the boundary of my x plus 3, right? So if we are within delta distance from 3, it is very, very, very reasonable to assume that delta is less than 1, meaning we are only going to be, that delta distance is not going to be around that x value is not going to be around 4, right? Because otherwise it would be in the 4 neighborhood, not the 3 neighborhood, right? So you want to just assume, it's very reasonable here to assume that delta is a positive number less than 1. Now, when that is the case, then we would say the absolute value of x minus 3 is less than 1, because the absolute value of x minus 3 needs to be less than delta, right? So that means that x minus 3 would have to be in between -1 and 1, or we can say that x is in between 2 and 4. Graphically, it will make sense to say whatever that neighborhood is, it is in between 2 and 4. That would be a reasonable neighborhood to look at, okay? So your delta is going to be a number so that x minus 3 or x would be in between, somewhere in between, but not further than 2 and 4. All right, well, if that's the case, then x plus 3 will be in between 5 and 7 when you add 3 to both sides, which means the absolute value of x plus 3 is less than 7. So this guy right here is less than 7. So we can say that 7 times x minus 3 is less than epsilon, so that x minus 3 is going to be less than epsilon over 7. Well, what are you going to claim your delta to be to make this thing work? That delta is going to have to be epsilon over 7, whatever epsilon is, because it is supposed to be an arbitrary number that someone just give you for all epsilon greater than 0. All right, so that is how we go and find the delta. In this case, actually, we would say delta is either going to be epsilon over 7 or something that it is going to have to be epsilon over 7, and it also have to satisfy the fact that it is less than or equal to 1. So we would say delta is going to be the minimum between 1 and epsilon over 7. And that is what we will choose our delta to be in the proof. Okay, so that is scratch work, just to come up with that delta so that we can show in writing the proof that there is such a delta. So here is the proof. Okay, so first we would say when we hit for all, we would say logically assume that it's an arbitrary number. There is a delta. Well, we got to show 1. So given that epsilon that someone just give you, that arbitrary epsilon, we would say, hey, I'm going to go ahead and let my delta be the minimum of 1 and epsilon over 7. Okay, that's why we did this scratch work, so that we can claim that delta. So we can logically prove in this statement here. Okay, now the next part is an if-then statement. How do we prove an if-then statement? We assume the if part is true. Then our job is to show that the then part follows. Okay, so next in writing the proof, we would say, well, let x be an arbitrary input in that delta neighborhood. And that means that x minus 3 is less than delta, and also x minus 3 is less than 1, right? Remember, because delta is the minimum of those two values. Okay, now since x minus 3 absolute value is less than 1, then x minus 3 is in between -1 and 1, or x is in between 2 and 4, so that absolute value of x plus 3 is less than 7. And you might be thinking, Didn't we do that before? Yes, we did in our scratch work. That's not part of the proof. So here we are writing the proof. So we are restating or stating the logical progression of how this works, right? All right, so now we just established that the absolute value of x plus 3 is less than 7. Okay, now we also know that the absolute value of x minus 3 is less than delta, and delta, so then the absolute value of x minus 3 is going to have to be less than epsilon over 7, because that is what we let delta to be, right? That we said choose delta to be that. All right, now if that is the case, then you can multiply by 7. And also, since this holds true, I can conclude that this is going to happen. Therefore, the absolute value of x squared minus 9 is less than epsilon as needed to show. Therefore, by the definition of limit, we have shown that the limit as x go to 3 of x squared minus 1 is equal to 8. We have done all that is required of us logically, meaning we assume that epsilon is an arbitrary value. We found a delta that will make this work. Therefore, by the definition, the limit is true. And that is how epsilon delta proof work.